Continuing our discussion of convective heat transfer for internal flow, we'd like to look at an energy balance for a differential slice of the circular tube that we are considering. So our differential control volume will have a width of dx, so this is the axial direction, and we will allow a constant mass flow rate to be passing through the control volume. We'll assume that on the left-hand side, entering the control volume, the temperature of the fluid, the mean temperature, is Tm, and we will in this case assume an inflow of thermal energy denoted by dq, which would cause a subsequent increase in the mean temperature by an amount dTm. To apply the first law to this control volume, we would say that the amount of thermal energy added to the control volume will equal the increase in total energy of the fluid within the control volume, and that's given by m dot c sub p delta t, where in this case delta t is Tm plus dTm minus Tm, which of course then gives me just the incremental amount of total energy m dot c sub p dTm. I just want to point out here that in this type of analysis, the rate term is coming from the mass flow rate, right? So this is kilograms per second. When we looked at the conduction aspect of heat transfer, we always thought of the rate as the rate at which energy was moving through a solid. So of course, in this case, we have flow moving through the control volume, and that is where the rate term is coming. So the rate at which this thermal energy is entering the control volume, the dq term, is equal to the flux term times the area, in this case the perimeter, the circular perimeter, which would be pi d times dx. And the heat flux term is given by Newton's law of cooling, though we note that in the most general case, each of these terms, the heat convection coefficient, the surface temperature, and the mean temperature, may all be functions of the axial distance. The value for P, again for a circular tube, which we will be restricting our discussions to, is given by pi d. Now, returning to the expression for the amount of energy that's being added to the flow and the corresponding temperature increase, and to that adding the expression for dq that we get from Newton's law of cooling. So since the left-hand sides of these two expressions are equal to each other, we can then equate their right-hand sides, and solving for the differential mean temperature term, we arrive at this expression. And this expression can be integrated to obtain an expression for how the mean temperature varies as a function of x. To do this, we'll have to consider a number of cases. There's two broad categories for the situation. First, if the heat flux on the tube wall is a constant, and for the case where the surface temperature is constant. And for each of these, we'll have to consider two different situations. The first is to consider the entrance region, where the heat transfer coefficient is a function of x, and then the location where past the entrance region. And the second will be in the fully thermally developed region, where h becomes a constant. So looking at the first of these two cases, where the surface heat flux is a constant, we would start with this equation, but then we can recognize that the Newton's law of cooling will allow us to rewrite this as just the constant term. So h times the temperature difference just becomes the constant heat flux. This term can then be integrated from the entrance condition into the tube. T sub m comma I is the mean temperature at the inlet, and we'll integrate that up to some axial position. On the right-hand side as being the axial position 0, going up to some arbitrary axial distance. And this will give us this expression, which shows that the variation in the mean temperature is a linear expression. And we can look at this on a plot. The expression here is valid from the inlet, where x equaling 0, all the way to, assumedly, the outlet at x equaling L. In the region where h is a constant, the expression for the heat flux will let us know that if h is a constant and the mean temperature is a constant, then Ts also has to be a constant. And that difference between the two of them is derived from Newton's law of cooling. So we see that Ts minus the mean temperature at any axial location is equal to a constant value of the constant heat flux divided by the constant heat transfer coefficient. So we see that this is not a function of x. But we find that in the thermal entrance region, the heat transfer coefficient is a function of x. So even though we have a constant heat flux, because of the varying heat transfer coefficient, we'll find that we have a varying surface temperature. So while the mean temperature increases with a constant slope, the surface temperature will change until we reach a constant slope of the surface temperature. We find that if we have a constant heat flux, that will result in a constantly increasing surface temperature with a defined slope as long as we are in the fully thermally developed region.